All right, let's try some cool synthesis problems here. Try them out. So let's see. 19.69a, taking cyclohexene, and then we're making this alkene. There's no E or Z to speak of because this side is symmetrical, so nothing to really worry about there. However, if we want to make an alkene like that, you know what I'm thinking is that we would want to make that from a Wittig reaction, where if we had this ketone would be the best way to do it, because then we could start with a primary alkyl halide and then make a Grignard, or why do I keep saying that? And then we could make our Wittig reagent from it, right? We could make the Wittig reagent, and we know that we can do, you know, the SN2, the SN2 here, and then of course the deprotonation. So it would work best with a primary alkyl halide. So then the first question is, okay, fine. You know, we could just assume that we have this Wittig reagent, but how am I going to make this ketone? Well, I think the first thing we would want to do is just add water across the double bond and then oxidize it. Now, since there's a plane of symmetry running through this compound, I don't have to worry about Markovnikov or anti-Markovnikov. There's no carbocation rearrangements that occur. So the easiest thing to do would be to just treat it with aqueous acid. And that's going to give me cyclopentanol. Did I say that when I meant cyclohexanol? So then I'm going to treat that with PCC or sodium dichromate, or you could use desmartin periodinane. You could use the Swern. Maybe we'll try the Swern again. So DMSO and oxalyl chloride, followed by triethylamine. And that gives us cyclohexanone, this compound. And now we just need to do our Vidic chemistry. And so all we're going to do is we're going to take this and we're going to treat it with our Vidig reagent. We're not going to show the whole Vidig synthesis. It's not asking us to do that. So instead of me drawing it as the ylid, since our book seems to be addicted to the ylene form, I'll draw it that way. Oops. There we go. And then 1, 2, 3. There we go. So Vidig reaction on the last step. And that's how you would do that one. And if you want to go over the synthesis of the Vidig reagent, well, you would start with, what did we say? You know, 1 bromopropane or 1 iodopropane. And in the first step, you would treat it with triphenylphosphine. And then the second step, you would treat it with butyllithium. All right, that's how you'd make the Vidig reagent. In that case, let's move on to 19.69b. So in this one, we're taking a geminal dibromide. So this is B. And we're taking this Gemini twins, right? We're taking this geminal dibromide. And somehow we want to end up with a dimethyl acetal or a dimethoxyacetal. This thing here. So we have an acetal. And we could just do a quick retrosynthesis of the acetal, right? This is an acetal. So going backwards from here, we know that we would want to start with this ketone. So this would be methyl cyclohexyl ketone, and then we would treat that with methanol, CH3OH, acid catalyst, and remove water, and that will give us the acetal. So then the question becomes, well, how do I get from here to here? Even if you weren't 100% sure, I'll tell you something right now. The only thing that you've ever learned in this class to do with a geminal dibromide is to make an alkyne from it. So if we take this and we treat it with excess sodium amide in ammonia, followed by treatment with H2O, that's going to give us the alkyne. So let's just draw the alkyne and then see if we can connect the dots from there. So I've got 1, 2 carbons. So I end up with this alkyne. Well, how do I get from here to here to this methyl ketone? Well, the methyl ketone is what you get when the enol tautomerizes. How do you make the enol? With a Markovnikov addition of water across the triple bond. So you need mercuric sulfate, sulfuric acid in water, and that's going to give you, I'll draw the enol. That's going to give you this enol, Markovnikov addition, right? And then the enol is not stable. It undergoes tautomerization to give you the desired ketone. And now that we have the ketone, it's just one quick step to make the acetal. So we've gone over this chapter. What do we need? 2 equivalents of the alcohol. So you could put this, times 2 if you want. I'd buy that. Or if you want to put a stoichiometric 2 in front of it like that, that works too. Then we need a catalytic amount of acid. And then we always put minus H2O because we end up removing water in acetal formation. So there you go. Hey, it's been a while since we've seen this in class. This is from chapter 9, the alkynes chapter. I know we looked at it in chapter 11 too, but not a lot. Okay, let's move on to C. So 19.69C. This is a cool one. We're starting out with cyclohexene, and we want to make this giant ring. So this 8-membered ring that's got 2 oxygens in the ring. So we've got one here and there, and like this, and then you've got a geminal dimethyl. Whoa. Anybody have any ideas about this one? Like, what functional group do you see in the product that you could do a retrosynthesis with?
An acetal.
Diggity darn, couldn't have said it better myself, right? I have an acetal, don't I, Lindsay, right? Because you've got carbon, oxygen, carbon here, and carbon, oxygen, carbon here. So this is an acetal. Acetal. And thus, if you do a retrosynthesis, the ketone you would start with would be just acetone, this, and then your alcohol would be this giant thing that's got 1, 2, 3, 4, 5 carbons in it. So 1, 2, 3, 4, 5, like that. That's kind of an ugly drawing, but I kind of ran out of space. I think a prettier way to draw it would be like this. Oops, we pretty that up a little bit so it would look like this. So we have our hydroxyl, then 1, 2, 3, 4, 5. There we go. So 1,5-pentane diol. Okay, so those 2 compounds put together are going to give us this acetal. Well, this compound has 1, 2, 3, 4, 5 carbons in it. And this compound has 1, 2, 3, 4, 5 carbons in it. So I would try to go from here to here. Well, the only way we know how to break open that ring is with ozonolysis. So why don't we treat it with ozone followed by DMS and just see what happens. Look what happens. You end up with 1. So here's our aldehyde. 1, 2, 3, 4, 5. Here's our second aldehyde. Now, how would we get from here to here? All we have to do is reduce both of those carbonyls, and you've got that compound, that diol. You could choose lithium aluminum hydride if you want. That's a 2-step process. You know what? Sodium borohydride doesn't get enough love. So let's put sodium borohydride. You could put methanol. You could put ethanol. You could put water. Let's pick methanol. And we have 1, 2, 3, 4, 5. We have a hydroxyl here and a hydroxyl here. So we have our 1,5-pentane diol. And then to make the acetal, all we have to do is treat it with the ketone. This is acetone, right? Acetone nail polish remover. A catalytic amount of acid. And you remove the water. And there you go. It's one of those problems that, I looked at it last night and thought, jeepers, that's a doozy. But then you just kind of do a quick retrosynthesis and you see, oh, well, if I've got 5 carbons here, it must come from here. And you can kind of do a quick retrosynthesis on that one. All right, question 19.73 has got a bunch of cool stuff in it. Let's just try the first couple problems. And we'll start with 19.73, A, where we're taking cyclohexene, so we have an alkene, and then we want to make this acetal, so this is cis on the ring. We're making this acetal. So, Lindsay said, okay, well, if I get an acetal, I can do a retrosynthesis on that, right? This is the carbon that's attached to both of the oxygens. And thus, if I do a retrosynthesis on this, it means I need to have this compound where I have cis 1,2-cyclohexane diol, this compound, plus your carbonyl compound is just going to be this, right? Which is formaldehyde, the simplest possible aldehyde that there is. So then the question becomes, well, how do I go from here to here? You have to do a syn dihydroxylation on an alkene. Does anybody remember any conditions to do a syn dihydroxylation on an alkene, or their favorite conditions to do syn dihydroxylation?
Catalytic amount of osmosis O4 and NML.
Yep, sounds good to me. So syn dihydroxylation, yep, sounds perfect. So let's put here catalytic amount of osmium tetroxide. And then we put in NMO as our co-oxidant in methylmorpholine N oxide. Perfect. That gives us the cis diol, which is added in a syn fashion, like that. And then the next step is what we just saw in 2 problems already. So lots of practice on, forming acetals today. So you would need your formaldehyde, catalytic amount of acid, and then you remove water. Okay, let's try one more. Let's see. I thought this one was also another really good one. This is 19.73b. Some of these problems are really interesting, like this one. So you start out with this compound. You have a primary alkyl halide. And then you got to add a bunch of carbons to it. So you end up adding what? 1, 2, 3 carbons. Let's see here. Oops. Ready? There we go. So we want to add 1, 2, 3, 4. There we go. In a methylene like that. This one, I had to stare at it for a second before I was like, oh, okay. There's kind of a key step in this one, in my opinion, based on what we know. And that is there's 2 key steps, really. Number 1 is that I would think about making this double bond from a Wittig, right? So that means retrosynthetically, you'd want to start with this, this ketone, right? And then you would just treat it with the Vidic reagent, which would just be this. We even saw this today, okay? So that would be the last step. That would be the very last step in the reaction if you could make this compound. But you see, this thing's got 6, 7, 8 carbons here. You get 6, 7, 8, 9, 10. So this is the 11th carbon, I guess, but you've got 2 carbons here that you've got to add. And so the question becomes then, well, how do I add those 2 carbons? Did anybody figure out a strategy on this one? I'm just curious. I think there's only one way to do it based off of what we've learned. Anybody? No? Okay. I think really the only way that I could think of to do this is to use a Grignard. And, would be to do another retrosynthesis step. So let me just draw another retrosynthetic arrow here and say, look, if you had, this is like the second key in my opinion. So let's see here, 1, 2 carbons. If you had this, right, because you can make a Grignard from this compound, you just treat it with magnesium. If you had this Grignard and you had this as your electrophile, this is called acetaldehyde, then it's going to attack here, and you're going to end up with a secondary alcohol, but you can oxidize that to the ketone. So this to me is like the first key step, and this is like the second key step. Later on we'll look at things that have, more than 2 key steps, but that's kind of the way I pieced it together. Was the hardest thing, I think, was coming up with this piece, knowing that you have to use acetaldehyde. And then the second most difficult thing is a Wittig, but usually my students get pretty rock solid at the Wittig after they've practiced it, for a few weeks. So let's pencil this down. What would the whole thing look like? I'm not going to write aromatic ring. Let's just write pH to simplify our lives. The first step is going to be to make a Grignard. So for that, we use magnesium. You can put a solvent if you want. You don't have to. It doesn't matter. So we're just going to put MgBr like this, or you can erase that bond and you can put it like this and put the negative charge here, positive charge here. That's the way I like to do it. It just helps me keep track of everything. So then you would treat that with the aldehyde, 2-carbon aldehyde. It's called acetaldehyde. It's one of the compounds that's largely responsible for a hangover. So let's see here. You would end up with something that looks like this. So this is the first step. The second step would be Just treat it with water or aqueous acid to add the proton to it, and you end up with this compound. Okay, now I think it's pretty abundantly clear what we've got to do. First thing is we've got to oxidize that secondary. You can choose whatever you want, like any oxidation conditions we learned. Some of my students really like the sodium dichromate. We can use that in this case, there's no problem. And that brings us to the ketone. And then the last step is just to do the Wittig reaction. Kind of running out of space here. So we would take the Vidic reagent with only one carbon in it, like that. And again, you could write that compound out like this as the ylide form, like that. Either way, this is the ylene, this is the ylide, they both work. And that's going to add the methylene to the very end of the molecule. And so our final product, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbons in it. And that's the whole synthesis. How many steps? Let's see. We got 1, 2, 3, 4. Actually, it's only 5 steps. It's not that bad, really. Okay, so what I'd like you to do before coming to class on Friday would be to go into the end of the chapter. So if I scroll all the way down here, and I think, there's a lot of good synthesis problems in here, but I think that one that would be fun to do in class is this one here. So we did the first 3 in here, and then maybe we could start with D through H on Friday afternoon, and then we could start chapter 20, which is the carboxylic acids chapter. And again, make sure you come to class on Friday. I know I'm saying that to the students who have the best attendance, but make sure you come to class on Friday because I'm going to be talking a little bit more about the chapter 19 quiz, which I'm still working on, but I have an announcement that I'll share with you about that.